How many piano tuners are there in Chicago? Sounds impossible without a phone book. Yet the physicist Enrico Fermi could nail the answer in under a minute on the back of an envelope. He once estimated the first atomic bomb's yield by dropping scraps of paper as the shockwave passed. By the end of this video, you'll do the same. Some quantities are too numerous to count or too hard to measure. Molecules in a breath, the mass of the oceans. We can't get exact answers and we don't need them. We aim for the order of magnitude, the right power of 10. Picture a number line in powers of 10. 10 to the 20th, 21st, 22nd, 23rd. If the true value is 10 to the 22nd, any answer between 10 to the 21st and 10 to the 23rd counts as success. We're hunting the power, not the digits. Fermi didn't guess, he reasoned. The method has two steps. First, identify quantities you actually can estimate. Second, build a relationship that links them to your target, then multiply and divide. One safeguard ties it together. Check the units. If the dimensions cancel correctly and leave the units you want, your chain is sound. Errors in individual guesses tend to cancel. Overestimates balance underestimates, so simple assumptions yield surprisingly reliable answers. Pianos. Start with Chicago's population, about 3 million people. Roughly 5 people per household gives 600,000 households. Say 1 in 10 owns a piano. That's 60,000 pianos. Now, how many tunings can one tuner do per year? A piano gets tuned about once a year, and the tuner handles maybe 3 a day, 5 days a week, 50 weeks a year. That's 750 tunings yearly. Now divide 60,000 pianos over 750 tunings equals 80. Call it about 100 tuners. The real number sits right in that range. Now pennies. How many pennies laid in a line span 1 kilometer? It takes just one step. The count equals the total length divided by the diameter of a single penny. 1 kilometer is 100,000 centimeters. A penny is about 2 centimeters across. So we divide 100,000 over 2 equals 50,000 pennies. A real penny actually measures 1.9 centimeters. So our crude guess of 2 centimeters lands within about 5% of the truth. The lesson is that the precision of your inputs matters less than the structure of your reasoning. Pianos are easy. Let's aim at the planet itself. What's the mass of Earth's water? The oceans are an impossibly complex shape, so we model simply a thin spherical shell wrapped around the globe. Earth's radius is about 6,000 kilometers. The oceans average roughly 1 kilometer deep, and they cover about 75% of the surface. So the shell's volume is 3/4 times 4 pi r squared times the depth d. Now mass equals density times volume. Water's density is 1,000 kilograms per cubic meter. Let's work in meters. The radius is 6 million meters and the depth is 1,000 meters. The volume is 3/4 times 4 pi times 6 million squared times 1,000. 6 million squared is 3.6 times 10 to the 13th. 3/4 of 4 pi is about 9.4. Multiplying everything together gives about 3.4 times 10 to the 17th cubic meters. Now multiply by the density of 1,000. The mass comes out to about 3.4 times 10 to the 20th kilograms. Rounding to the nearest power of 10, that's 10 to the 20th. The accepted value is 1.4 times 10 to the 21st kilograms. We're in the same neighborhood and we nailed the right order of magnitude. From pennies to the breath of an ancient philosopher, same method. Here's the showstopper. What's the probability that none of the molecules in your next breath were also in Lao Tzu's dying breath 25 centuries ago? We need 2 pieces. First, one breath holds about 3 times 10 to the 22nd molecules. Second, the atmosphere. Model it as another thin shell, about 10 kilometers thick, wrapped around the Earth. One breath is roughly 10 to the minus 3 cubic meters. That's about 1 liter. The whole atmosphere is about 4 times 10 to the 18th cubic meters. So the probability that any one molecule from your breath lands back in that single dying breath is just the ratio of the breath volume to the atmosphere volume. The chance that one particular molecule is not from his breath is the breath volume divided by the atmosphere volume. That's 10 to the minus 3 divided by 4 times 10 to the 18, which is about 2.5 times 10 to the minus 22nd. So the probability of a match per molecule, P, is 2.5 times 10 to the minus 22nd. For all n molecules to miss, the probability is 1 minus P raised to the n. Here's the useful trick. The limit, as n goes to infinity, of 1 minus a over n, all raised to the n, equals e to the minus a. To see why, take the logarithm. N times the natural log of 1 minus a over n is approximately n times negative a over n, which equals negative a. Our exponent a is n times p. That's 3 times 10 to the 22, times 2.5 times 10 to the minus 22, which is about 7.5. So the probability that none of his molecules are present is e to the minus 7.5, roughly 5 times 10 to the minus 4, or about 1 in 2,000, essentially 0. You're almost certainly breathing his atoms right now. Fermi estimation is a thinking habit, not just a physics trick. It builds intuition, sanity checks official numbers, and powers decisions in engineering, business, and tough interviews. The errors cancel, the structure carries you, and the few known anchors beat paralysis in the face of uncertainty. Unanswerable questions just became answerable. That's your new superpower.